Hello and welcome, everyone. Today we're diving into some fascinating research material from Dr. Sudandra S.G. This is all designed to help teachers and educators get a really solid grasp on one of the most powerful pieces of technology in modern computing, the graphics card. Together, we're going to peel back the layers and see how a chip no bigger than a postage stamp can perform calculations on a scale that is just almost impossible to imagine.
All right, so here's our roadmap. First, we're going to try to wrap our heads around the sheer universe of calculations a GPU deals with. Then we'll get to know the two different brains inside your computer, the CPU and the GPU. After that, we'll take a journey right inside the graphics processor itself, uncover the magic trick behind its power, something called parallelism. And finally, we'll look at how this technology is shaping our world way beyond just video games. You know, to really appreciate what makes a graphics card so special, you first have to understand the problem it was built to solve. The demands from modern software, especially something like a super realistic video game, are absolutely staggering. We're talking about a scale of computation that's hard to even comprehend. Take a look at this number, 36 trillion. That's how many calculations a high-end graphics card can churn through every single second, just to run a game like Cyberpunk 2077. Now, a number that huge is basically meaningless on its own, so let's try to put it into a perspective we can actually understand. Okay, how do you picture that? Well, imagine you took the entire population of Earth, and then you found about 4,400 times more Earths, also full of people. If every single one of those people did one calculation every second, all working together, they would just match what one of these little devices can do. It's just mind-boggling. So that brings us to the big question, right? How is that even possible? How can one tiny little chip be that powerful? Well, the secret isn't just about raw speed. It's about a completely different way of thinking about work. And it all starts with understanding that your computer actually has two very different kinds of brains. And to explain this, there's a fantastic analogy that is just perfect for the classroom. It's the idea of jumbo jets versus cargo ships. If you want to understand the difference between your computer's central processing unit, the CPU, and its graphics processing unit, the GPU, this is pretty much all you need to remember. So think of it like this. The CPU is your jumbo jet. It's incredibly fast, super flexible, and it's designed to handle a few really complex tasks. You know, your VIP passengers, high-priority cargo, and get them where they need to go as fast as humanly possible. The GPU? Well, the GPU is a massive cargo ship. It's not as quick, but it's built for one thing and one thing only, moving an unbelievable amount of simple, identical stuff all at the same time. Let's just break that down a bit more. The CPU, the jet, has just a few really powerful cores. It's the jack of all trades, running your operating system and handling complex, varied instructions. The GPU, the cargo ship, is a specialist. It has thousands of simpler cores that are absolute masters of doing simple math on a massive, massive scale. So it's never about which one is better, it's about using the right tool for the right job. Okay, now for the fun part. Let's take a journey inside the cargo ship itself. We're going to peel back the layers of the graphics card and zoom all the way in from the big circuit board right down to the tiny little engines that do all the work. And you'll see it's organized almost like a city with a really clear structure. And this hierarchy is everything. You start with the whole graphics card. On that card sits the main GPU chip. That chip is then divided into a handful of graphics processing clusters, or GPCs. Think of these as neighborhoods. Inside each of those neighborhoods are several streaming multiprocessors, or SMS. They're kind of like the building managers. And finally, inside the SMs, you have the actual workers, thousands of specialized cores doing all the heavy lifting. Now here is a really fascinating little secret from the tech world. You might go to a store and see 3 or 4 different models of graphics cards, all with different names and different prices. But they could all be built around the exact same physical chip. So, how does that work? Well, it's all thanks to a very clever manufacturing process called binning. See, making these silicon chips is so complex that tiny microscopic defects are just unavoidable. But instead of throwing away a chip that has a tiny flaw, manufacturers test it. If one of those little neighborhoods, a GPC or an SM, is defective, they just turn it off. A chip that comes out absolutely perfect becomes the top-of-the-line model. A chip with a few sections disabled gets sold as the next model down. It's a brilliant way to make sure almost nothing goes to waste. So we've seen the hardware. We know there are thousands of cores. But now we need to understand the principle that makes them so incredibly effective. It's a concept that computer scientists call an embarrassingly parallel problem. And yeah, it's a funny name, but it is the absolute key to everything a GPU does. This is the perfect job for our cargo ship.
Think about creating an image on your screen. The color of any one pixel doesn't depend on the color of the pixel right next to it. They're independent, so you can calculate the color for all of them at the exact same time. That is the definition of an embarrassingly parallel task, and GPUs crush these problems using a method called SIMD, single instruction, multiple data. Let's use an example. Say you've got a 3D model of a hat that's made of 14,000 individual points, or vertices. If you want to move that hat, you don't need 14,000 different complicated instructions. No, you only need one single instruction, something like move this point 1 inch to the right. Then you apply that one instruction to multiple data points, all 14,000 vertices. The GPU then tells all its cores to execute that same command at the same time, each on its own little piece of data. That's it. That's the power of parallelism. Now, modern GPUs use an even more advanced version of this called SIMT, which stands for Single Instruction Multiple Threads. The basic idea is exactly the same, but it adds a little more flexibility. What if on our hat, some of the points needed an extra little calculation, maybe to change color? With SIMT, those specific threads can take a slightly different path or take a moment longer, without making all the other thousands of threads wait. It makes the whole process way more efficient for the complex stuff we see in the real world. So, as you can probably guess by now, this incredible power to chew through massive repetitive calculations isn't just for making video games look beautiful. It has totally revolutionized a bunch of other fields you might not expect. When you look under the hood of these things, game rendering, training an AI, even cryptocurrency mining, you find they all share the same DNA. They all rely on doing billions of simple, repetitive calculations. Training an AI is basically just multiplying huge tables of numbers together over and over and over again. These are all embarrassingly parallel problems, and they are the absolute perfect job for a GPU. The crypto mining craze a few years back was a textbook example of this. The core task was basically generating random numbers. Think of them as lottery tickets, by running the same mathematical formula again and again, hoping you'd find a specific winning number. And because every guess was totally independent of the others, a GPU could run 95 million of those attempts in parallel, every single second. So in the end, understanding the GPU is about so much more than just graphics. It's about understanding a fundamental shift in how we approach computing. In a world that is generating more data than we know what to do with, that cargo ship model of tackling huge problems in parallel isn't just a neat trick anymore. It's an absolute necessity. From scientific research to the AI that's becoming part of our daily lives, this is the engine that's going to be powering our future.